our viewership is through the YouTube packaging later. I just click this button and we have a new feature that streams everything. I think that is now enabled. I'll just double check things there and then we can get underway. Yeah, appears to be working fine. Great. Technology works. Fantastic. Share my screen and we can get underway with Flower Monthly. Perfect. Well, thank you all for joining us to this Flower Monthly. It is jam-packed with three fantastic speakers. We've also got a number of updates from the point of view of Flower to share with you. My name is Nicholas Lane, and thank you for joining us. So the agenda is as follows. As always, I'll give just 5 minutes of a few of the happenings within Flower since the last time we ran a monthly. And then we have three speakers. And so we are really got a great cross section of federated research and techniques today. We have Boyo Fan. He is from the University of Helsinki. He is going to be talking to us about an interesting approach to using LoRa in the context of federated fine-tuning when people need to use foundation models. So I can't wait for that. We're then going to have Taliha Melabu from the University of Massachusetts Amherst. He is going to be diving into a topic of how can we tune the carbon footprint of machine learning within this federated regime. And then at the end, we've got Demetrius Tripelis. He is a member of the Flower Labs team, and he's going to be showing us how you can use Flower under Google Cloud Platform. So that's our roundup for today. And so before we dive into those three speakers, let me give you a few updates. So one update is that next week is the Machine Learning Systems Conference. It'll be the 8th edition of this conference. It's happening in Santa Clara, and Flower is going to be there. And so I'm going to be there with Lorenzo Sani, and we'll be trying to connect with all the variety of researchers doing fantastic work at the sort of boundary of machine learning and systems. But primarily, we'll be there to present formally the Photon system, which is an extension of Flower to enable the scaling of training to large language models and the application of that training to pre-training. And so Photon sets a brand new SOTA in the domain of efficient and robust pre-training of federated LLMs. We will be presenting that work there at MLSys. So can't wait to see so many of you next week. Those of you who saw Wired in the last 10 days would have seen an article by Will Knight. Will Knight wrote a feature on a lot of the things that Flower is doing because it's starting to enable us to migrate away from data centers into using other kinds of compute networks together. And we're starting to be able to see how that can actually be applied to a variety of new kinds of models. One of those models is called Collective One. And a key part of this article was how Flower is working with Vana using user data where it's completely opt-in data that's collected by Vana DAOs combined with privacy preserving training to build a foundation model called Collective One. So check out that article if you're interested in those topics. And if we reach back a bit further into the month that's just gone by, a large number of the Flower team has been engaged in the public outreach to sort of educate and share the different kinds of open source tools that we're all building. And so one of these members of Flower was William. You would have seen William on a number of Flower monthly events in the past. He's been working closely with folks at MIT and connecting with networks of interested folks in the sort of topic of decentralized AI in New York to do a number of presentations that you see highlighted here. Additionally, we had Daniel. He was a guest and a sort of featured speaker as part of a new virtual event that was really popular. I think there was around 10,000 people joined this virtual event organized by Matt Hartman called GLOSSAC. This was sort of a global get together of open source AI organizations of all kinds. And Daniel talked to Matt about the potential of federated learning. We also have another key member of our team, Mohammed Nazari. He is an expert in privacy and robustness and security as it pertains particularly to federated. And he's been giving a number of talks around the world recently. He visited physically the Mohammed bin Zayed University in the Middle East, and also giving talks to universities in Italy on sort of topics that he's an expert in. These are things that have also happened in the past 30 days. Finally, I'd like to highlight some of the outreach that Chongshen has been doing. Chongshen is part of the Flower family, and he's been connecting in particular with the Python open source community as it sort of pertains to things like PyData, PyCon Germany. And so Chongshen also appeared at a very popular podcast this month. And so he's really been showing people how you can use Flower to do federated learning really much easier than people often imagine as possible. One last sort of shout out to some of the things we've been doing lately is at iClear. This is one of the key conferences in machine learning. It happened about 10 days ago. And so I was there along with Javier, Lorenzo, Alex, and other folks. We ran iClear Social in the topic of decentralized AI. We had folks showing some of their techniques to each other, presenting ideas about how there could be more community initiatives, which is something that Flower cares a lot about. We were also there primarily because Flower had a key piece of technology that had been accepted as an iClear oral that was presented. And this is a technique called DEF. It is all about the enablement of decoupled embeddings during large-scale training. It enables important, capabilities under a federated regime, but it also is quite it raises the bar of quality of models that can be trained even in data center scenarios. So that is sort of a whirlwind tour of all the things Flower has been up to in the last month. With that, I'm going to hand over to our featured speakers. So our first featured speaker, I'm really stoked to hear from. His name, as I mentioned earlier, is Boyan Fan. He is at the University of Helsinki, and he's going to be talking to us about his LoRa-based approach to federated fine-tuning. And so over to Boyan. I'm really stoked to hear your talk.
Yeah, thanks, Nick. Thanks for having me. I'm going to share my screen. Is it good to look?
Yeah, it looks good to me.
Okay, cool. Okay. Hello, everyone. My name is Boyu, and I'm from University of Helsinki, and I'm here to present our work recently. It's just published in ACM Transaction on Internet Technology of last month. And the title is Hey LoRa, LoRa Heterogeneous Federated Fine-Tuning for Foundation Models. First, I have a short bio to introduce. And I'm a final year PhD student, which we call doctoral researchers at our university. And my supervisor is Professor Pan Hui. And for now, I focus on efficient and heterogeneous federated learning. And I also do some research about edge and pervasive computing. And for now, I have published papers on ECCV, IEEE, PERCOM, big data, and journals such as TMC, TOSN, and TOIT. I also serve as a reviewer for PERCOM, continuous 4 years, and IGCAI, TMC, and some journals about bio and other intersection areas such as JB, HI, and IoT journals, etc. So first, let's start, and I assume that everyone here is very familiar with what is FL, and we just to repeat them and as an introduction to what we are going to talk. First, FL is that we have one server, we have some clients, and the model is always initialized by the server, and the clients will conduct a local update with their private data to update the global model. And you can check here from the different colors. Which means that the different colors, they are represent for different knowledge. And after the aggregation, they will be integrated to the global one. So they have contributed to the global one. But we should notice that the model here is always fixed because it's a universe one. It's initialized by the server and it's shared by all parties. However, in real-world settings, these clients might have varying resources, which means that they might have different processing ability to train models, such as this. Some devices, they might have like a very powerful resources with GPU-equipped server, but some of them, they might just purely resource constrained like a Raspberry Pi. So the problem will arise like several problems. One of them is structure issues, which means that the faster one is always need to wait for the slower one. And also the server needs to wait all of them because the conventional FL assume that we need to do the aggregation once all the updates are collected. And so this is also lead to another problem like resource wastage or etc. And moreover, with the increasing model size, like nowadays the LLM, the very big foundation models, we need to do very heavy communication overhead because FL always assume that we need to transfer the model parameters or gradients. So this is another problem. And yeah, let's see what happened. This left is the left one is the traditional weight averaging. And what we want is that for this Raspberry Pi, we want to give them a small model. And for a laptop with more resources, we want to have them it have like a full model or a bigger model. But the problem that is here, the first one is that how can we aggregate models with different structures? It's very apparent to see that they have different model structures. And for the conventional, we just do the vanilla element-wise averaging. But now, since the parameter shapes are totally different, we can do that. So the first question is how can we aggregate? And the second question is that can we use light structures to achieve model parameter exchange so that we do not need to transfer the heavy parameter tables. And let's move to the preliminaries. And first, we want to introduce the rank for people who are not very familiar with that. So rank means that low rank adaptation. So this is a parameter efficient fine tuning method, which only use the LoRa parameters, which only updates LoRa parameters, while the original model, like this blue one, they are keeping frozen. So by this way, we can just reduce trainable parameters significantly because we can just train these two matrix A and B. We can keep this frozen, and by introduce this very key parameters rank R, we can slightly adjust this model complexities. For example, if we give R a very small one like 4, it might be a light model, but if we give R a very big one, it's also can become very similar with the original one because it depends on the R. And so they can see the forward path become the original one is just a WOX. Now we can have this B and A. So we just keep this frozen and train the B and A. So this is LoRa. And for another preliminary is the problem definition. So since we are aim to perform federated fine tuning across clients with heterogeneous LoRa modules based on the resource of devices, which means that, as I mentioned, for example, maybe for GPU equipped servers, we can give the R very big, like a 2, 5, 6. And for a Raspberry Pi, we can just give them 4. So since that, we will have this heterogeneous LoRa models. And we want to have this global model to update like this. So NK is here, is the amount of data of each client, and N is the total. This is very similar with the traditional fed average one, but we can see the WKR is different. They have different shapes. So this is a challenge here because R is different. So this is the what we introduce our method here. Our method is HeyLoRa, and we propose two variants. The first one is called HeyLoRa Pad, which is a very straightforward idea because you can see from the name, we just pad them. And you can check from here, there's a client, assume we have client 1 and client M. And client 1 has the rank is R1 and client M is RM. But they are both less than the global one. So global one is like a full model, but this is like a truncated model to tailor for their resource constraint. And we just padding them to make them align with the R global so that we can send them to the server side to do the element-wise the averaging because they have the same parameter shapes now. And what we are padding is depending on, we propose this context-based padding function, which will be introduced very soon. And after they do the element-wise averaging, we will truncate them to their original shapes. And like this, we will give them R1, RM, and they send back to the client side. So this way, we can achieve aggregations even if they have different original models. So the context-based padding is also very interesting. So you can check, we can just apply different functions to them. The first one is the maximum. So if we want to pad a row like this, if we want to pad a row, so the P is always calculated by this column. Like if we want to have the maximum, the maximum of this column, then we will pad as a P for that. So if we want to pad a column, we want to have the maximum of this row to get this P. So this is our strategy. And also there's another strategy called adjacent function. So this is also very easy. We just copy and paste like this. If we conduct this strategy, we just copy this column to this, and we just copy this row to this. So this is a very straightforward way, but we will illustrate them in the experiment later. It works very well compared to just do the zero padding. And next is the rank-based adaptive aggregation. So there's an empirical evidence that shows the model with a larger R generally achieve better performance to a certain limit in LoRa because we have more model parameters, we can have the more training well. But based on these insights, we will assign larger weights to models with higher R values like this. So instead of just consider the amount of data, we introduce another dimension, which is R here. So with this design, the model with more parameters, they will make a larger contribute to the global model. And the models with few parameters, for example, the Raspberry Pi, they might just have the R equals to 4. And if they have a bad or not very well training result, they will also minimize the potential harm to the global model because the R is very small. But this will still providing valuable contribution by this different rounds of training. So this is the path. But let's check the pros and cons. So the pros is that this variant, this HeyLoRa path is very easy to conduct and it's very easy to compute. But the cons is that, with the padding, the structure modification happens. Because for now, pre-release R equal to 4, now they maybe R equal to 128 sometimes. So this might destroy the original learned stuff. So this is the cons. So the question is that can we achieve model aggregations without modifying the model structures? So this is another variant we propose called HeyLoRa KD. So let's have a very short recap of what is knowledge distillation. So knowledge distillation basically is just there's a big model called teacher model, and there's a small model called student model. And the teacher model will do will output logics, and the student model also have the logics. They will compare to each other using a KL divergence loss. to minimize this loss so that the student can be performed as good as the teacher models, but they have much less parameters. So follow this idea, we propose HeyLaura KD. So you can check from this figure, instead of adjusting the rank values, we just keep them unchanged. This is R1, the server side is also R1, RM. But we propose a mutual distillation process so that this knowledge can be sharing with this process. So instead of performing element-wise parameter averaging, the knowledge are sharing with this process. I will give the details soon. So let's check. So we call this a deep mutual learning based aggregation. So let's assume that we have M LoRa modules. So this procedure on the server side begin with performing a forward pass with public datasets, so that each model will generate their logics, right? Because they are different structures. And we will first calculate the conscious, like here. The conscious is calculated very similar with the idea of the rank-based adaptive aggregation we mentioned, in HeyLaura pad. So we also consider the R value here. So the loss function becomes here. And so this is also a very similar idea with the traditional knowledge distillation, but we applied here. So the first item is the traditional cross entropy loss, and we introduce this KL divergence loss to make each client, they will have to minimize the distance between the conscious, because the conscious, they have all the knowledge from the different clans. And now we want to each clan to as close as to this conscious. So in this way, after the multiple round of training, each clans, they will have the knowledge globally. They will have other knowledge. But instead, we do not modify the model structures. So this is very interesting. And LE loss just as a cross entropy loss. And we also use a beta, a hyperparameter to control how much knowledge they will learn from others. Yeah, so this is a fine-tuning problem, fine-tuning parameters we will mention in the experiment. And so that's basically all the design. And for the experiments, we have like two tasks. One is image classification task. Another one is NLP. We use the very traditional one, CIFAR 110 and IMDb and SST2. For the baselines, we select the traditional Fed average, and for Fed IT and SLoRa, these are two methods that equipped with LoRa, but they more or less is the vanilla combination with LoRa with the Fed average stuff. So this is we call that model homogeneous approaches, because they are not allowed, they have different model structures. And for the model heterogeneous approaches, we select HeyLaura. This is a very similar work with us, but as I mentioned, this is just a zero padding one compared to our HeyLaura pad. And this four are another method that allowed heterogeneous model. So for the models, we use the Vision Transformer and Distilled Bird. They are also, they all downloaded from the Hugging Face. And for the settings, we select 20 clans with their ranks. This is LoRa rank, equally assigned with these four values. Let's check the performance. So if we check this performance on 4 datasets, we can find that both the HeyLaura pad and KD, they outperform the rest baselines. And especially the KD is also performed slightly better than the HeyLaura pad. And you can also observe the HeyLaura pad works continuously better than the HeyLaura, which is just a zero padding. So, and also compared to the standalone, our results is also very close to the standalone, which means that if we combine LoRa and our method can achieve really good results. And for the rest experiment, we changed different heterogeneity levels, because previously we just considered these four, but now we give them to minimize to simulate the real world. We give them this different value ranks from these different distributions, and we sample them, and we find them. We give them the results here, and we also find that the HeLoRa KD outperformed the rest. So this is interesting. And an interesting observation is also can be followed here. So if you check the uniform and the normal one, the uniform is more sparse and the normal is more centralized. But our method, you can see from here, compared to HeLoRa, it has better performance in this uniform one than the normal one. This is because the knowledge distillation one can give different knowledge sharing from different rank values. So if R is like very small one is 10, and this is 100, they can also give the 100 knowledge to the 10 one. So even in this very sparse distributions, HeLoRa KD works very well compared to this normal one. And another one is we also try apply LoRa different layers. This is the QKV for the transformer-based model. And you can check if we apply the QKV or we apply QKV, this is a better performance than just a standalone for QKV single. And you can check from here. We also have a very small training parameters compared to the full fine tuning. And yeah, we also check the different padding functions for the HeLoRa pad. As I mentioned, there are max, minimum, and adjacent. And compared to the 01, the 01 is the baseline HeLoRa. And you can check, actually, the adjacent one, just the copy and paste can achieve a much better performance, not much better, but slightly better than the other padding strategies. That just implies that the model parameters is also equip some knowledge. So if you want to give them just a zero padding, they will have some chaos after the aggregation. So it's better to just copy and paste to maintain their original knowledge. And for the other is that the hyperparameters analyze for the beta. The beta is how much knowledge sharing from others can involved. So you can check from here that different datasets actually have different optimal values. The CIFAR10 has the 0.6, but IMDb is just a half. This is because that for the datasets, for a more complex datasets, the knowledge they require is more. They need more knowledge from others because it's more complex. So it need more knowledge from here, which means the beta need to be bigger. So this is this one. And we'll also verify the different client number from 20 to 60. You can check from this figure that our HeLoRa KD always is more or less remain the same. But for HeLoRa pad, it's just drops because maybe if the heterogeneity is much bigger, the padding will not work as much well. And also for the rest one, it works much lower than us. So this is this, and we also do some ablation study for the rank-based adaptive aggregations, which is the R value. So you can that with or without it. With it, it has a slightly better performance than without that. So yeah, and also do some two case studies. So the rest, the above one is just the transformer model. So we check if our method can work on non-transform models. So we try the ResNet 50, and it also works well because LoRa can be directly applied to convolutional layers. So this also applied to our work. And another case study is that we check the non-classification task, which we use the squad datasets, and it also works well. The only need to modification is that we need to change the class-based logics to the position-based logics. So we just need to slightly adjust our loss function. And that's all. So the conclusion is that we propose HeLoRa. It is a novel federated fine-tuning framework designed to address system heterogeneity challenge. And we also have two variants. One is the HeLoRa pad and the HeLoRa KD. They both employ different strategies to achieve LoRa heterogeneous aggregations. And an extensive experiment shows that HeLoRa perform well in NLP and the CV tasks. And for the future work, I think first we want to explore more efficient padding strategies to minimize structure changes. For example, if the heterogeneity is very serious, how can we handle that? And the next is try to perform KD without the public datasets. This is the one of the limitation of our method because we need to rely on a public dataset. And the third one is that we want to extend our evaluation to a broader range of foundation models because for now we just use the vision transformer and some DistillBERT one. It's quite small compared to the nowadays one. So we want to check them like the GPT and also the Llama if it can work with our method, our framework. So yeah, that's all. Thank you. So if you want to check more, you can have me on this this QR code. Thank you.
Thank you. That was great. So then anyone who's watching right now, feel free to pose any questions right now, and we can get to you. I see someone has posed a question. I'll just ask. I mean, I'll ask this one on behalf of the person, but feel free, other people, just to raise your hand. Or I've also got the different channels open, so I can hopefully see questions as they come through on X or YouTube or so forth. But so our first question was, thanks for the insightful talk. Is it possible for you to share the slides? So
Sure.
yeah, okay. I guess
How should I share the slides? May I
I think
ask?
they could just email you here, or if they have difficulty finding you, they could mail me, and I can get them in touch with you.
Okay,
That's
just
fine.
feel free to email me. I'll send you the copy.
Yeah, great, great. We have another question here from Adam. I'm just going to enable him to talk. So Adam, your microphone is going to just come online, and so you can ask your question.
Perfect. Can you hear me?
Yes.
Yep, we can hear you.
Awesome. Thank you for a great presentation, Boyu. It was really, really interesting. I was just wondering, you dealt with the problem of resource heterogeneity between the clients. Did any of your evaluations touch on data heterogeneity, so label shift or feature shift among the clients?
This we consider that because for this results you can check. We just follow the traditional non-ID distribution here with this distribution with 0.1. This is a very common setting for federated learning papers, I assume. And but for this paper, our main focus is not for the data heterogeneity. We focus on the resource, or we call that system heterogeneity. So if you want to check the data heterogeneity, I think maybe and this is one of the, I think, future direction to combine this framework with the data heterogeneity. I think it's a more interesting topic. But for now, we just use the traditional one to follow. So we do not have any very special design for that. Yeah.
Cool, cool, fair enough. I'll see if anyone else wants to ask a question. Yeah, I guess not. I'll just ask a question here. I was wondering, is there any backstory to how you came up with this idea? I'm always curious about how people kind of come up with their ideas. So were you thinking about how do you do fine tuning, or were you interested in LoRa and how it could be used into federated learning, or what was the impetus for you inventing this?
Well, I think I have some papers accepted about model heterogeneity previously, and before I doing research about federated learning, I also do some, I can mention the edge computing and pervasive computing. So I'm very familiar with the hardware. So we always do the Raspberry Pi and some
Yeah.
NVIDIA the development kit. So I wonder, yeah, so I just know these are heterogeneous. So if we want to apply federated learning on them, it might be have problem because they have different processing ability.
Makes sense. Yeah,
Yeah.
cool. Great. Well, then I think we should move on just in the interest of time as well. So thank you for the great talk. Amazing stuff.
Thank you.
Yeah, thank you again. Um, so then our next speaker is online, is right here. He is based in the University of Massachusetts Amherst. He is Talha Mebu, and he has been examining, I assume, a number of things, but what really caught my attention was his work in examining the carbon footprint in the context of federated learning. It's something that I personally have done a bit of work on in the past, along with some other collaborators. And so I'm always curious about how things have been moving on. And so yeah, thank you for joining us today. It's fantastic to have you here, and I'm really interested to hear your talk today.
Thank you so much. I hope you can all hear me. All right. Can you all see my slides?
Yes.
Okay, perfect. First of all, thank you so much, Nick and Flower Labs, to have me here. It's a pleasure. My name is Talha, everybody. I'm a PhD candidate at University of Massachusetts Amherst. And today, the work that I will be presenting, as Nick mentioned, is basically how we can optimize for the carbon footprint of federated learning. This work is still under review, but the authors, besides me, that worked on this paper are Noman, Jesus, Mike, and David. This is a joint collaboration between MIT, Telefonica Research, and UMass Amherst. A little about myself. Obviously, I work at UMass at the Sustainable Computing Lab, and we mainly work on like designing sustainable or energy efficient solutions in like data centers, edge computing, cloud computing, and my research focuses also towards like how we can make the computing, like specifically machine learning, more sustainable and more efficient. With that, I think I would start my presentation. And the big question, obviously, is like, why is this problem even important? Like, why do we even require to like make the federated learning more carbon aware? And the answer is basically, I think Nick mentioned Photon. I've read that paper like a lot of times, honestly. And that paper, and along with like some other studies that we can see here, shows that we're running into the problem of like having confined data at one location. And in order to have access to more public data, we obviously have to go public. And then that essentially means a more collaborative, distributed environment for training. And what's better than federated learning to do that? So as we see from this graph, we show that by 2028, if we keep training the LLMs model as we are right now, we will probably run into the problem where we don't have enough data in private settings, and we need to access the more global, more public data. And federated learning, while preserving the privacy of the data, is the best fit to do that. Um, However, existing techniques generally focus more towards how we can like increase the performance of the federated learning or machine learning models. They generally overlook, or they ignore the fact that there's a big carbon footprint associated with that training, as the energy that we use in order to train those federated learning models generally come from the uh, electric grid, which operates on like coal or gas or like those non-renewable resources. So this graph actually shows the comparison between uh, uh, the carbon footprint of centralized versus the federated learning settings, and we can clearly see the difference that at certain locations, the the carbon footprint is way higher compared to the centralized. So there's a need that in federated learning, there's that given its importance to like train foundational models in the future, and its increased significantly larger footprint compared to the centralized, there's a research gap that we need to make this federated learning more carbon aware and reduce the carbon footprint while maintaining the performance so that we can make the training more sustainable. And that is basically where our system comes in. We build this system, which is a joint optimization for the carbon efficiency, the model accuracy, and the training time. And essentially, we are navigating this trade-off, which is a three-way trade-off between the carbon efficiency, the model accuracy, and the training time. Okay, so before I actually talk about how we actually implement stuff, how we use Flower or the design of our experiment, I really want to focus on this very important point, how the carbon varies over time, because as I was listening, like you mentioned, Nick, that what is the idea behind the project? How did we actually come up with the intuition for this project? And the idea was basically like we looked at the energy sources, we looked at the carbon intensity, which is essentially the how much carbon is being generated when a certain device using 1 kWh of energy to perform certain task or computation. And from this global carbon intensity graph, we can see the dark brown areas are basically the ones where the energy that is being generated uses either coal, gas, or like those non-renewable resources, so that the carbon intensity is higher compared to some of the greener regions, which uses, for instance, France uses the nuclear energy to nuclear sources in order to generate electricity, and hence uh, the carbon intensity in those regions is smaller. And the idea is basically that if the carbon varies over time and across space, we could potentially use this spatial variations or these temporal variations in our advantage while we're making the selection in the federated learning. So that was our basic idea, or like the basis of like where we started. If you look at the left bottom graph, this shows the carbon intensities for 3 different locations across the globe for 3 different days. And we can see that the carbon actually varies significantly between the two regions at the same time. And also the carbon varies significantly for the same location at different times. And that variation can be up to 30 times difference in spatial variations, and up to like 6 times variation in the temporal variations. Uh, and that basically was the major motivation behind using these carbon variations in order to optimize for the carbon footprint of the federated learning, given the nature of federated learning being so distributed that we can actually opt to go for a more distributed environment. Okay, so here I present the actual design or the solution of EcoLearn. So I think it's very clear now that how do we make the selection of the clients is based on the carbon emissions. However, we can't just solely make the selection based on carbon, because uh, it is very likely that always the low carbon clients would have lower utility. Now, utility is like a known concept in the literature, which essentially tells us like how important a certain client is. So we need to make sure that we're selecting clients which not only reduces the carbon, but also enhances the performance of the training. So the first module that we look into is the client selection, which actually selects clients based on their more utility and less carbon. Um, the second module comes from the fact that since the carbon varies and the utility of client is actually larger, or is greater in the initial phase than in the later part of the training, we can basically scale the number of clients during the training process. So we don't really have to train on same number of clients throughout the whole process. We can scale our idea is that we can scale more during the initial phase, which is basically called the critical learning period, and then basically dies down. The number of clients that we select dies down eventually because there marginal increase in the accuracy. And doing that, not only we enhance the performance by selecting more high utility clients in the beginning, we also reduce the overall carbon footprint because the average number of clients that we select over the training period reduces because we lower the number of clients at the end phase of the training. And the third basically is to eliminate the factors that impact the performance in a negative way, and that is the stragglers. Boyu also mentioned in his presentation that how stragglers can overall elongate the process, especially in the synchronous aggregation, that we are always waiting in the heterogeneous system. We're always waiting for the slowest client. So in order to avoid those stragglers, in the past, people have been using the over provisioning factor, which is like we over provision clients by a factor of, let's say, 30%, and then we wait for the first, let's say, n number of clients to respond, and that we're hoping that we're avoiding the stragglers by doing so. We saw an opportunity there, again, the carbon variations. We saw that what if we increase the number of over provisioning during the low phase carbon period and then reduce the number of clients that we over provision during the high carbon period. And that essentially makes our system even more carbon aware. So we introduced essentially in EcoLearn, but we introduced the carbon awareness in the client selection. We introduced the carbon awareness into client scaling and the straggler mitigation techniques. And essentially, that helps us to increase the performance or maintain the performance while significantly reducing the carbon footprint of the FL. Okay. So this is the system design that we're using. Obviously, I think the major thing that I want to talk about is how we use Flower framework in our system, given I'm presenting at Flower Monthly. So I think as I have discussed, we have three major modules. How can we select clients? How can we scale clients? And how can we over provision? We require obviously the carbon intensity information in order to do that, associated with each client or location. As a matter of fact, we need to define some of the configurations. I'm pretty sure you're familiar with like how we can configure the federated learning settings in a certain way. And the most important thing is how we can use the utility information in the global aggregator along with the accuracy of the model in order to allocate the critical learning period within the server. So the way it works is that we define our own custom criterias based on like which specific clients do we need to select. That basically tells that information into the client manager, which samples those clients, give that information to the configurator in the averaging, the configure fit, as people are familiar with that, which basically configures the very specific client for the next round of the training based on the utility, carbon, and the fact that if certain clients have already been selected before or not. And all of this information is being kept at the server in the Flower framework, the aggregator. And essentially, the server returns the list of the clients that needs to be selected in the next round of the training. And doing so repeatedly over rounds of training, we overall reduce the carbon footprint while we're trying to maintain the accuracy of the model. For the evaluation results, I will go through them quickly. I believe the major result that we have is that we reduce the carbon footprint by a factor of 11 to 14% for different levels of non-IID or different levels of distributions of data. And I think the major carbon savings that we see is for like the extreme non-IID settings. And that is like you can see the carbon agnostic approaches are using significantly more or emitting significantly more carbon compared to the carbon aware techniques, which is one of them is EcoLearn and its sister policies. We reduce the overall carbon footprint significantly while we maintain the accuracy as seen in the graph on the left. Which takes me to the last point, which is rely on the Pareto frontier, which essentially means that we optimize or we efficiently optimize the carbon compared to the accuracy, compared to all the other baseline policies. So it's like if you just select clients based on the utility, yes, you will have better accuracy, but your carbon would be bad. If you're just randomly selecting clients, you probably would not have good accuracy or carbon. As a matter of fact, just selecting clients based on the carbon is not good either, because then you will be get into your model will introduce bias in the system and will affect the performance. So the best way is to basically go moderate and like select both of these metrics into the consideration while selecting the clients. So as you can see, EcoLearn basically efficiently optimizes both of these, or navigates this trade-off between accuracy and the carbon efficiency. And yeah, with that, I would like to thank all of you who are listening. If you have any questions, you can, or want to read this paper, look into the actual results or methodology, you can go on my website. The paper is linked there. Or if you have any question, my email is also attached here. So you can, if you have any question you want to contact me, you can do that. And with that, I would like to thank Flower Labs, Nick, again for inviting me here, for an opportunity to give the talk, and the collaborators for their contributions and their work.
Great, thank you so much. Wonderful stuff. So just the same as we ran earlier, if anyone who's part of the Zoom webinar, you can raise your hand. I'll unmute you. You can ask a question. I'll browse around some of the other channels to see if people paste their questions in there. Yeah, so feel free if anyone, this is a good opportunity to ask questions about this work. I don't see anything coming up yet. I guess I'll ask a question, and that was back on slide 8. You had different baselines, and so I'm sure you mentioned this, but so random is random client selection under like Fed average or something, I suppose.
Yes, that's true.
Let's see. And did you have any evaluation where it would kind of correspond to the carbon emitted under a maybe some I guess a selection policy that is based on where the data happens to be. I guess it'd be somewhat of a simulation, right? Data might be in 7 hospitals, and so you could imagine the data spread under that sort of regime, and then you could assign carbon maybe to actually real hospitals and then see what it would be like. Because that wouldn't be random. You'd be training a model based on, well, it depends on what the type of selection criteria is, but you probably would be doing it maybe equal, or there's different things that happen in a real federated system. So I wonder if you have a sense between an actual operating system and the carbon of that system, and maybe random in your one, to see the gain.
Well, I didn't really quite catch the last part. If you could repeat that, please.
Oh, sure. I was just thinking under us. I mean, cross-device, often clients are selected at random, but I guess under cross-silo, you often have a specific. You might move between the clients, but it's quite deterministic or prescriptive. And so do you have a sense of, like, in that type of setting, what the carbon gains might be?
Right. I think for the baselines here, for the random, we just thought, how if the server has access to 100 clients, how we can just randomly select, like, let's say 30 out of those, and just look at the carbon emissions of those. And as far as like the I think one of the major concept of this paper was also to show that having these intelligent client selection policies can actually help and not degrade the performance. Because there's this general notion in the community that having this intelligent client selection policies introduce bias, because we're generally looking into like specific clients because we want to reduce the carbon or cost, as a matter of fact, like any other metrics of cost. So doing this, we also show that we can have arbitrary notion of cost. In our case, that is carbon cost, for instance, but this could also be battery consumption or like energy, or like it's like an arbitrary cost metric. So I don't really understand exactly the like or I can't answer like what would be the sense of like different criterias here, but I'm pretty sure like using some intelligent client selection, we could take it further, like a notch further. We can overall reduce the carbon emissions further if we look into other metrics.
Yeah, perhaps my question was ill-formed. I was just sort of thinking on the fly what would happen under a cross-silo setting. But anyway, just thinking about it, and most of the cross-device settings, you have training runs that last for weeks, as Google and other folks have shown. And
Right.
so you probably can, when you interact with certain devices, get the same model, but for vastly different carbon footprints, assuming there is variation in your population, which there probably should be.
Right.
Yeah, cool.
When you say cross-device, are you assuming that those devices are kind of co-located in a similar region, so there are less variations?
I don't know. I haven't really thought about this as much in a practice. I mean, I guess it depends on how big your population is and how much flexibility you have to interact with each one and still arrive at the same model. But on a certainly these large scale cross device scenarios, you would imagine that flexibility does exist. So that's interesting. I'm rambling on here, but we do actually have another question that I can read out. And so the question is, do you assume clients use different compute resource? And are you selecting also based on the client's energy consumption? So that those are two questions. Do you assume clients use different compute resources?
Right.
What would you say?
So, in our system, obviously we have this heterogeneity in terms of data, which we're assuming that there are different data distributions. We do not have experimental results or evaluation results on like different types of GPUs or like the heterogeneity in terms of the system that we're using. However, we're positive that we can certainly evaluate this system on like different types of GPUs or hardware, as a matter of fact. For the second part, which is the energy consumption of the device. So in this regime, there are a couple things. One is like the energy's carbon efficiency, and the other is the energy's carbon intensity. So we essentially want to make sure that the computation's carbon intensity, which is essentially like how much carbon dioxide are we generating per cycle of computation that we are performing. And that is a factor of like how much computation that we're performing per cycle, given the kilowatt hour of energy that we're using, and basically the carbon dioxide that we generate given the kilowatt hour of energy. So the point here is that in this evaluation, we do not look into the actual energy consumption of the specific devices, but we assume that given this carbon intensity, which is kind of like the inverse of the carbon efficiency, we're capturing that essence. So like if a certain device, obviously there's an assumption that we're using 1 kWh of energy on that specific device. If that changes, would that affect overall our results? The answer is no, but that would change the overall value of the carbon intensity, but the metric still remains the same. So I think we have looked into like if we need to add that discussion. We have that discussion in the paper, by the way. So if you want to go read, like we have this discussion in the paper. But do we want to evaluate our results with like varying energy consumptions? We realize that that would not overall affect the final results.
I see. Cool. Yeah, this is one of these issues that there's a lot of depth to issues like this because it sort of expands outside of outside of computer science, to be honest, and starts looking at things like where does energy get generated and all the other secondary things that are quite critical. Awesome. Well, I'm glad you're really working on this because I think it's really important. So thank you so much for joining us today. Perfect. Great work. So let me share my screen and we can go to our final speaker. So our final speaker is Demetrius. He's my colleague here at Flower, and he's been working with a lot of folks out there. One of the folks he's been working with intensely is Google Cloud. We've had a lot of requests for being able to use Flower and Google Cloud together. And so, yeah, he's been chatting to a number of the engineers there to see how do we make this experience better. He volunteered for today's session to show us a bit about how Flower and Google Cloud look together. I think there's a bit of a demo or a broader discussion about this. And so I'm really eager to see what he can show you all, and hopefully that enables a lot of great experiments and systems and POCs to be possible. So over to Demetrius. Great to have you here.
Thank you for hosting me. Let me share my screen. Oh, I need to, yeah. All right. So, second. Are you seeing the screen?
Yeah, we can see your screen fine.
Perfect. Right. Hello, everyone. My name is Dimitri. I'm a research engineer at Flower Labs. Today, I'm going to run you through how to use Flower on the Google Cloud Platform. So basically, how you can run any Flower application using Google Cloud Platform and along with the Google Cloud, Google Kubernetes engine. To start with, so just give a little background on how we have revamped Flower Platform lately. So right now, it's relatively easy to deploy or draft or create any Flower application you like. So you can have a huge LLM, or you can have a very tiny deep learning model, and this can be directly connected to a superlink, which is communicating with a couple of supernodes. So in other terms, the superlink is like a server acting as a server who is orchestrating the entire execution of the federated learning application throughout a number of devices. This device can be a mobile, a desktop, or a server, where a supernode is being hosted. So the idea here is that you can create, through the Flower platform, you create any application and just really easily submit it to a superlink that is already waiting for some Flower application, some Flower jobs to be run, and then distribute them down to the supernode, which are being hosted or deployed on dedicated devices. So the different runtimes right now that are being supported by Flower, the first one is, of course, the simulation runtime, so which is ideal for research purposes. So you can develop a Flower application to experiment with, create an ad hoc or a new idea and explore right away with the simulation engine. The nice and the beautiful thing with Flower is that once you have the simulation engine up and running and the Flower application up and running with the simulation, you can easily use exactly the same instructions and exactly the same structure of the Flower app and deploy it on a different on an actual devices, distributed devices, and this can be done through the Flower deployment runtime. Finally, the same application also can be run with a third-party runtime. So other platforms that support Flower, the Flower instruction, the Flower applications, and they and can run Flower applications from scratch as well. So the core idea here, what I want to show is that you can start from simulation, go to the deployment, and then use another third-party platform to run exactly the same application that you defined from the very beginning while you're experimenting with Flower. So right now, I want to dive a little bit more on the Flower deployment side and what are the and how it's working and what are the different components and how everything interacts with each other. I'll start by giving an overview of the deployment runtime. Right now, through the Flower platform, we have achieved to enable different runs to run simultaneously on the same infrastructure. The Flower CLI has been optimized and has been revamped in order to support very easy commands on how to run, create, run, and generate create artifacts from the existing runtime. There is also user authentication, node authentication that can be supported out of the box. And of course, Docker deployment along with Kubernetes deployment. And last but not least, with the recently introduced Message API, which is actually a highly optimized way to communicate throughout the network of devices, the Flower devices. And we can support any type of communication protocol and of course, highly optimized security protocols as well. Just to give a little bit also background on the CLI and why is this so important is because, for instance, by running the Flower new, you are able to create a new Flower application. You create a template that can be run from simulation to deployment, as we saw in a couple of slides back. Why is this important? It's important because from research code, you can run right away into production code. This can be done through the Flower run. So once you create the template, you define your own instructions, your current client app, server app, and other scripts that you want to run over the network, over your Flower Federation network. And through a simple command, which is a Flower run, you can easily run and deploy and execute the Flower job. Last but not least, we also have other commands that are really can really give you more insights on how the federation performs. This can be done through the Flower log, where you can see real time the logs of active Flower runs. There is the list, which basically Flower list that gives you the statuses of the different Flower jobs, and finally, of course, the Flower stop, which basically can terminate or interact with a current actively running Flower run. Overall, we have simplified the Flower CLI in order to make it easier from going from research perspective to deployment in basically in very few commands, very easy, straightforward, in few commands. Here, what I want to also dive a little bit deeper is a little bit what's happening under the Flower deployment runtime, under the hood of the Flower deployment runtime. To be precise, as we saw at the very beginning, we saw there are two core components, right? Flower components. One is a superlink, the other one is supernode. So superlink acts as a server in simple terms, and supernode acts as a client in other terms. Under the hood of the superlink has three APIs. The first one is the server app IO API, which basically communicates with the server app. The server app here is the script, let's say, or to make it easier, that contains what is the logic, what are the instructions that will be executed on the server side. The Fleet API coordinates execution across the connected supernodes, the supernodes that are connected to the superlink. And lastly, the exec API is the one that receives execution tasks by the user. So basically, a user, when he wants to perform, he or she wants to perform and run a Flower job, then by using Flower run, then this Flower run is being propagated to the exec API. Finally, we have the supernode, and the supernode sits on the client side. However, is the one that is receiving the instructions from the superlink, but the actual execution communication happens on the client app. So the client app is the one that contains all the instructions that are specific to the Flower job we are actively going to run. I didn't go into the port side, but basically we just want to show that by default, these ports that we have available are the default ones from 91 to 93 are used by the Superlink component, and 94 is used by Supernode component. Of course, they can easily be changed and configured depending on the requirements that you have for your deployment. Two more components that some other under the hood, things are happening on the Flower deployment runtime is the two different modes that we have. One of them is called sub-process mode, and the other one is called process mode. We're going to dive into both of them. And what I'm describing here is the sub-process mode. So assuming we have a Flower Federation that consists from one server and two clients, the containers that we need in order to execute our Flower deployment or Flower infrastructure in this sub-process mode contains one superlink and two supernodes. As you can see on the right-hand side, we have the server. The server is a single Docker container. We build one single Docker image and we spawn one single Docker container that contains both the superlink and the server. On the client side, similarly, we have one single dedicated image. We create one image and then we spawn another container, and we have supernode client app both within the same container. And this happens for every other client in our federation. Again, this is the sub-process mode. So basically, the server app and superlink are co-located or appear together on the same container. And again, the supernode and the client app appear together on the same container. The next one, which is the process mode, and this is the one we're going to use throughout our deployment on the Google Cloud platform, consists of a little bit more containers. And the reason is that we are isolating the execution of the different components and subcomponents in our federation. So again, on the same example, we have one server and two clients. The containers we need here is is a little bit more. One is the Superlink, and one is for server apps. So we have dedicated containers and specific images and dedicated containers for each one process. And then we have 2 supernodes and 2 client apps. So one image for supernode and one image for the client app. So and this is going to run on dedicated containers. The reason we're doing this isolation is because it can give us a little bit of flexibility on how to isolate resource management and give us a little bit also more control on how we provision resources during the execution of our Flower job. And again, moving forward, we're going to focus more on the process mode, even when we do the deployment on the Google Cloud Platform. So now, so far, we have seen what are the core components on the Flower side. Now we're going to dive a little bit more on the Google Cloud Platform and how everything is put together in order to make sure we can have an active deployment of Flower on GCP. Just to give you a little bit of background, what is some core concepts that we need to be a little bit familiar with is, first of all, the Google Artifact Registry. So the Google Artifact Registry is, we can think of it as a space or a blob storage where we save images that we want to use during our deployment. Kubernetes is the orchestration tool that's going to basically pull from the artifact registry the images we want, and then deploy the containers of dedicated pods in our infrastructure, in our resources. One more item that we need to actually emphasize here is that throughout this deployment that we're going to show shortly, the entire deployment is happening through the Google Kubernetes Engine autopilot mode. So the provisioning of the resources and the automatic deployment of the pods is happening using the autopilot. There is also another mode that's called standard mode, but we're not going to cover it in this guide. I also want to give a little bit of background on necessary Docker and Kubernetes Engine CLIs that we're going to show shortly and use throughout this demo. So on the Docker side, there are 3 core commands that we need to be familiar with. One is the Docker build, where we build the dedicated images we need for the Flower application. There's a Docker tag, basically where we tag our image with the Google registry that we want to upload our local Docker image, and the Docker push, of course, where we upload our local image to the container, the Google registry. There's also, of course, the gcloud CLI, where basically through which we configure our local Google Cloud SDK. There are a couple of, I'm not going to dive in each one of them, but the core idea is how we interact with the Google Cloud infrastructure. So how we perform authentication, how we receive the credentials in order to be able to submit jobs to GCP and related works. Finally, there's also the most critical one is the kube control, which allow us to interact with an active Kubernetes cluster. And the core idea here is that we configure the current context, basically the current Kubernetes cluster we want to run our job, and then we apply the YAML files, or where the YAML files are actually Kubernetes or deployment files we're going to use and are specifically recognized by the Kubernetes engine in order to do the deployment of the pods. And lastly, is the get service Superlink service. This is specific to Flower, and the reason is by naming specific, the Superlink service, basically when we deploy the service, the Superlink service or the Superlink component, there is an IP, an external IP that we want to interact with. And in order to get this IP, we need to find out how what is the IP assigned to the pod of the Superlink component, and we can get that through the get service. We will show that shortly through the demo. Right now, just to give a final overview, what we're going to achieve, and throughout this exercise and the demo side, we basically have already created a project that's called Flower GCP. This one is basically contains the control plane, so the Kubernetes server that orchestrates entire execution, and then we're gonna deploy basically 3 nodes, one dedicated for the server, which consists from the Superlink and server app, and 2 more nodes that consist of super nodes and client app for each one respectively. What we show on the connected lines are the ports that we saw at the very beginning of our presentation, where how the user interacts with existing Kubernetes cluster, and how the nodes, the clients or the super nodes interact with the Superlink through which port and which service. Let me share me 1 second. I'm gonna switch. Hopefully, let me see how can I do this quickly. So is this? Sorry. I'm trying to find. Can you see my screen here with the Google Cloud Platform?
We see, yes, is welcome, Dmitry.
Perfect. All right. So what I want to show here is what we have created. We have created the Flower GCP project, right? And we have on the left-hand side, we have a couple of controls. What I'm going to go into is the compute engine, and then I'm going, in the Kubernetes engine, and then I'm going to the cluster, right? So there is a cluster, and in the cluster, we have created already the Flower NumPy example. So what we're going to run through is we're going to showcase how you can deploy a simple NumPy example on GCP. So if we press on this one, it's going to give us an overview of what is the region, what are the default zones, what are another configurations for the specific cluster. One item that we have done already is actually creating the pods. And the reason we create the pods is because it takes some time to initialize them. So we have pre-created them. And as you can see here, we have basically 6 pods already deployed. One is client app, the one is the Superlink server app, the Supernode, and client. And since we have all these pods deployed, I'm going to show in real time how we can achieve in general interaction with the Google Cloud Platform. On the left-hand side, if you can see I hope you can see my Visual Studio here. Is it?
We see the web page with this listing of systems.
Yes, I want to, let me change screen sharing. Okay, let me share this one. Okay, hopefully you can see this one now. Right.
Yeah,
Yes.
we see it.
Perfect. Okay, so what I want to go over is, so we have created with Flower New a very simple Flower NumPy example. As you recall, there is a client app, there is a server app, there is a task that I want to run, and then there are dedicated client app Docker file and the dedicated server app. So what we need to do at the very from at the beginning is we need to generate the specific Docker images that we want to deploy the containers with. So the idea is that we compile those, and then through the Docker Docker build, we compile them, we tag them with the registry, and then we push them to the Google Cloud. And as you can see here, just to give also another overview of the different help commands we can use, we have created the Flower NumPy example, and basically here's the build and the tag and the push. Now, one more thing that we need to cover, which is sometimes not clear, is again how we configure the Google Cloud SDK. So the idea, as we saw previously during the talk, is how we get the credentials, how we make sure that our local Google SDK interacts with the existing Google Cloud Platform. So what we're doing here is we're getting the credentials from the project we saw earlier, or the cluster, excuse me, we saw earlier in the Google Cloud UI. And then we get the current context in order to make sure that we are actually pointing to the correct cluster. Then we enable the artifact registry. This is actually where we're going to push our local client app server images. And then we create the Google registry where this push will happen. After we authenticate our local Docker, we build our client and server app images, we tag them with the respective registry, and in the end, we are actually pushing those images to the Google registry. Last but not least, what I showed before is basically we show 6 pods already deployed, and this can be done through the kubectl apply, where we pass the YAML files that we want to deploy on the Kubernetes cluster. And what we want to run right now is we're gonna run this command, assuming everything already is deployed. So by running, maybe I can actually make it a bit bigger. So if we run this, so we already know that the current context is pointing to our Flower NumPy cluster. So what we want to get from the Superlink service is this external IP. This external IP allows us to interact with the remote Kubernetes cluster, and we take that and we go to our project TOML file. This is pre-filled already, but we take this and basically we put the external IP in this address. By doing so, we allow our local Flower CLI to interact with the GCP deployment we have created, and what we're gonna run right now is basically run the GCP deployment. As you can see on the left-hand side, we have created this one. Yeah. And as you can see on the left-hand side, basically this address, we're running in the insecure mode because we can still run everything on TLS side, but right now for simplicity, we run on the insecure side using non-encrypted communication. So what I saw on the right-hand side on the terminal, you'll see that we have submitted the job on the Google Cloud, and then we have 2 clients, of course, and then we're gonna run for 3 rounds, and the entire execution flow shows basically the results we get from every other round. So this can be extended to any other Flower application you have, any other custom Flower application that you want to run. So it's not specific to this particular app. So that I'll definitely suggest going and trying it out on the application you want to test out. Let me get back to the previous one. And then let me. Is the slides visible? Are the slides visible?
Yes.
Okay, perfect. Thank you. So one more item that I want to emphasize here is the Flower close deployment. So far, what we show is basically how we have been able to deploy a cluster that is on a specific region and belongs to a specific project. Now, what we can easily extend to is run Flower across different regions and different projects, and of course across different clouds. So as you can see on the right-hand side, you see a project that is deployed in Japan, another one in Middle East, another one in North America, another one another project that is running on AWS. So this everything can be done through vRPC infrastructure and networking, and basically be able to run a Flower job across many different complicated scenarios or infrastructure. Lastly, but not least, I want to emphasize that we're happy that we are actually recently also launched our pilot program, the Batch 3, and we are open to any suggestions that, for instance, if you want to run a production workload using GCP, feel free to reach out, and then we're happy to get you throughout the entire pipeline and how to manage to do that. And the applications are open, and we are more than happy to help you run your Flower application, or even test out testing your Flower application into a more production setting. To summarize, throughout this presentation, what we have seen is the Flower deployment runtime, so different runtimes that Flower can currently support, from simulation to deployment to cloud, and to many other third parties. Some very core CLIs, like how you create a Flower in your template, how you run the template, and many other CLI tools that you need specific to the GCP cluster, which is how you build your local Docker images, how you push them, you tag them and push them, how you configure your Google SDK, and the kube control. And we focus again on the process mode. So basically, every other container, we create especially dedicated image for every other component, the subcomponent, and every other image is running on a dedicated container. We have also put together a very comprehensive guide on how you can run Flower GCP, which is in our framework documentation. And it would be great to test it out today and try out your different applications you want to test. Yeah, and then room for questions.
Excellent. Thank you so much. That was great. We're running a bit low on time, but if anyone's got a quick question, feel free to just dive in here, and we can answer them for you. Yeah, if there's any, but if there's no questions, we probably can just sort of start to wrap this up. I've got to say that we've had a lot of people wanting to use Google Cloud, both researchers who are working with partners who have their data already in Google Cloud, or the organizations already signed off on using Google Cloud. So it makes sense when they want to build federations of these environments. It makes sense to sort of run Flower with Google Cloud in those settings. We've also worked really hard with the Google Cloud security team to have a sort of a combination of methods that you can't find in other settings. And then, of course, you mentioned a lot of the production scenarios that people have asked for. Yeah, but that was perfect. I think I don't see any questions firing in, but people can follow up with you on our Slack. Through the pilot program, we've helped various kinds of organizations, big companies, startups, research labs, a variety of them. So yeah, so thank you very much. That was awesome talk and demo.
Thank you, guys. Thank you.
Then
Sure.
I will transition to final slide for today, which is an invitation to come to our next edition. We run Flower Monthly every Wednesday, every Wednesday of the first week of the month. So the first Wednesday that arrives in the month. It's always at 1600 UTC. So we're trying to balance time zones with the various parts of the Flower community. If you're interested in participating, just reach out to me. We can get you scheduled, find out what you want to share with folks. If you're online ever and you want to ask a question, one of the ways that's pretty effective is to use the Flower Monthly workspace and the Flower Monthly channel. I again just want to say, thank you to all our speakers who had fantastic talks today, from Tara and Bo and Demetrius, and yeah, wonderful Flower Monthly. So thank you, all three of you, for coming today, and thank you everyone who dialed in via X, LinkedIn, YouTube, and the seminar. So yeah, thank you so much, and take care, everyone. Bye.
Thank you, guys.
Bye.